all the participants and dear students. Welcome one and all present here on the fifth session of day 3 of ATAL sponsored 1 week offline FDP on unlocking the future, exploring the transformative power of 5G and beyond. Organized by Electronics Engineering Department, Rajki Engineering College, Sonbhadra. It gives me immense pleasure to introduce and welcome our eminent speaker, Dr. Amit Kumar. He is from IIT BHU Varanasi. Now, I would like to welcome him with a plant. I kindly request Mr. Deepak Shigroha. Welcome Dr. Amit sir with a plant. Oh, sorry. Mr. Atul sir, please. Deepak. Thank you so much, sir. Dr. Atul sir received BTech degree in Electronics and Communication in 2023, 2013. Sir, thoda sa hai bas. And MS degree in Electronics Engineering in September 2015 and PhD degree in Information Engineering at from Italy. Uh, from 2018 to 21, he was with sir, he is with Vodafone chair at Dresden University of Technology, where he was a research associate. He is currently an assistant professor in Department of Electronics Engineering, IIT BHU. He has been director of ATAL Medico Tech Solution Private Limited. He founded the company for the development of wireless medical devices for intensive care units, India, a technology startup for design, optimization, and operation of the medical devices. His main area of research includes 6G, V2V, that is vehicle to vehicle, V2X communication, IoT, Industry 4.0, robotics, wireless, cellular communication, synchronization errors, joint sensing and communication technology, AI techniques for end-to-end prediction and critical quality of services, new radio, massive MIMO, orthogonal frequency division multiplexing, generalized frequency division multiplexing, IoT, Internet of Things, and 5G and beyond. Sir, we are very glad to have you here. Thank you so much for accepting our invitation. Sir, you are requested to kindly start your session with the title, Importance of Futuristic Technologies, Next Generation Wireless Communication System, and kindly enlighten us with your kind words. Thank you, sir. Over to you, sir.
I hope, sorry. So as professor introduced here, so my name is Atul Kumar, working as an assistant professor in the Department of Electronics Engineering, IIT BHU. I am also the chairman of IEEE Communication Society UP section on this. So before introducing on the topic, so I did my BTech from private college. I am highlighting this part because the person who are doing the BTechs is not from IIT. They have many more opportunities also. So I did a BTech from a private college, JP University of Engineering Technology, from 2009 to 13. Then I did my masters from Politecnico di Milano in Italy. I receive Invest or Talent Scholarship. There is a program by the Ministry of Italy for 2 years of my master's program from 13 to 15. And then from 15 to 18, I did my PhD again from the Politecnico di Milano. The topic of communication comes under the Department of Information Technology. After completion from my PhD from 15 to 18, I went Vodafone Chair Mobile Communication System, TU Dresden, led by the Professor Gerhard Fettweis. If you Google it, the Professor Gerhard Fettweis is one of the well-renowned professor in the field of communication. I worked there 3 years as a group leader, and then I joined IIT BHU. One of my key motivation to come here and joining of IIT BHU also that I am from Sonbhadra, so my hometown is here, and that is one of motivation to join IIT BHU to work in our hometown. So I will start the presentation. I will give you not too much technical direction, but at least give you the vision that in which direction we have to do the research, what is the outcomes, and why we need to do that. This is the key aspect. So, and I will try to motivate you yourself to do the research, not only the academic point of view, many more on the industrial point of view, to have a entrepreneurship mindset, so that you can do something regarding the startups. So as sir mentioned, so I have one startups during my PhD is ATAL Medicotech Solution Private Limited. Then I have another startups we just started on the anti-drone system. So we are developing a radar system for military, and that how we are going to detect the enemy's drone. So I will during the talk I will give you that what are the potential area in these directions we can investigate regarding this. The entrepreneur point of view also is very challenging areas, and giving you the idea with the timeline also, that when we have to do this, the aspects. So yeah, so to start with, if you want to do so if you want to look more that what are the research we are doing, this is our lab, the Information Control Communication Lab under the IIT BHU Department of Electronics Engineering. So if you are interested, you can also visit the website of our lab, is ICC lab, and you can see that what are the different direction we are working, what are the different project we are dealing, and what are the different status we are doing here, and more regarding the research information here. Now I will start this presentation. So you can see the outline of my presentation. So very specific on the two segment only. One segment that why we are doing now for vision of 2030. So because we are thinking that what we are doing the research is going to implement into next 10 years. So that's why I am keeping highlighting the first part of outline, that what is the current requirement in 2030 point of view. That's the urgent need we need to do now, and there is a need research also beyond 2030 point of view. So core on the research aspects, that maybe next 20 years we are going to be in this direction. So I will give you also on the highlight on these directions. Beyond 2030 point of view, you can see two core technology we are targeting. One is the quantum technology we are targeting. Lot of you can see nowadays hype regarding the quantum technology. Government is also pushing lot more on the quantum technology. We are doing much ahead from these topics. What we are doing, I will tell you also on this aspect. And one more topics we are targeting 2030, you can say 2040's point of view on the molecular communications. To the very specific, I am saying that as an electronics engineer, we are reaching very close to the Moore's law, that number of transistor is increasing, and then we are predicting in the future then the processor is going to be based on the chemical processor. Then how we are going to use a molecular to help for our communication aspects. So regarding that part in the beyond 2030 visions. So first I will start with the 2030 vision point of view, what we are doing and what we are doing beyond that also. So I don't know why it's not working, this pointer here on the screen. So ये screen पे काम नहीं कर रहा. So it's fine. So basically if you see the 5G is 2020. Basically in the 5G, that is I need to reach it, right?
Yes.
But I can use on the back side. Yeah. So if you see the 5G, we have the 2020. So basically in the 5G they specify 3 groups of the communications point of view: enhanced mobile broadband communication, massive machine type communication, and ultra reliable low latency system. So the whole motivation of 5G, that we are going to classify the different use cases, services under these 3 categories, and then we are doing the research around these 3 categories. Each 3 categories has their own KPIs requirement. So we are developing the technology under this requirement of the KPI. Now moving from 2020 to 2030 vision point of view, you can see what we have, the 3 existing technology, we are extending this. So either we are extending enhanced mobile broadband, massive machine type communication, and ultra reliable low latency system become a hyper reliable low latency system. Now apart from the extension of 3 existing technology, 3 new technology added also. One aspect is the integrated sensing and communication, integrated AI and communication, and ubiquitous connectivity. This ubiquitous connectivity part is very specific to the Indian point of view, and there is a professor in IIT Hyderabad, Professor Kiran Kuchi. He is one of the leading expert to promoting this part, especially in the Indian context, because India is a country of demography where we have a lot of hills and forest regions. So provide a uniform connectivity point of view. So he is proposing the technology especially on this part, is also leading the ITU on these parts. Now we are working very specific on this part, integrated sensing and communication. So my core research area in 2030 point of view, what we are doing to do very specific here on the integrated sensing point of view, and we are also dealing that. So as I explained you before, so existing 5G 2020 on 3 verticals, they extended this in 3 new groups, and the new technology additions are integrated sensing and communications and other tools, right? And my whole presentation is first part of the presentation is going to focus on integrated sensing and communication. Why we need integrated sensing and communication, what is the applications, and what is the challenges on this. Now beyond 2030 point of view, the technology, as I mentioned, in the quantum technology. In the quantum technology, basically there is a 3 verticals technology, you can say. One is on the quantum sensing point of view. Sensing is a generic information that we have to sense the something. We have to detect the signals. Now the existing sensing systems works on the electromagnetic phenomena. Then what is the limitation of that, and how we are going to improve with the quantum, or why we need a quantum sensing, that's we will also discuss in the second part. What are the potential application? One of the potential application you can see in the medical field of the quantum sensing application. Second aspect, again, what is the importance of quantum communication aspect, why we need a quantum communication, and the third aspect of the quantum technology is the quantum computing. The quantum computing parts is more towards the development of quantum computer. Lot of race in the world wise, that who is going to develop large qubit quantam computer. So there is a 2 big player is Google and IBM. They are fighting, but still what they have only 124 qubit quantum computer. Very specific, I am saying 124 qubit is very less number, and if you want to solve the real time problem, we need at least 10,000 qubit quantum computers, and the 2 players are working. Recently one more company has a quantum computer, you can say the middle level quantum computer is a Honeywell. Actually Honeywell acquired a startup company from US, and we are in the touch with the founder of that startup company in our technology. So his company is acquired by the Honeywell, and they have also the quantum computer around 64 or 74 qubit quantum computer on these directions. So quantum computing means how I am going to do the challenges on the computing is the operation of the computing point of view. So these 3 verticals, I will focus very generic on the quantums, giving you the more sense on the sensing and communication aspect, very specific on here. The third aspect, as I mentioned here, on the molecular communication point of view beyond 30 vision, the key aspect here that now everything is based on the chemical, then how I use my molecules or to do the communications, starting from short distance communications to the longer distance communication. Now if you see the molecules are communications, so my organs become a cellular structures concept. So we are relating with the biology combining with the communication on this area. So now I will start on the detail point of view, that in the first topic on the integrated sensing and communication. So this is our team working on the integrated sensing and communication aspects. We have PhD students and the combination of postdoc students also. Now giving you the vision of the integrated sensing and communication. So if you see the existing aspects of the enhanced mobile broadband massive machine type communication or ultra reliable system, existing of this has a new in 2030, while having the two addition, AI and the sensing. Technology parts, they are adding only the AI concept and the sensing aspect here. So how I am going to combine now the existing communication with the sensing. So now we need a system that is capable of doing the sensing and the communications together, and then we have to understand the challenges on this, but why the key motivation, that if you look around the 6G point of view, you can see depending on the use case and the requirement, there is a lot more aspect where you can immediately point that okay, this parameter is used by the sensing, right, this parameter is used by the communications, right. So they have the KPI that include both sensing parameter and the communication parameters. So and that's why we are saying that if we are going to combine the sensing and communication, then only if we can achieve this kind of requirement and fulfill this kind of requirement, because applications demand this requirement. So how I am going to fulfill this requirement if I am going to develop a system that is capable of doing the sensing and the communications together. Now sensing and the communication has a application both indoor environment and the outdoor environment. They have both well known applications. Again I am trying to narrow down to go on the technical point of view. Here my focus on the outdoor environment point of view. If you see on the outdoor environment point of view, now my sensing is become a radar. So I am not using any physical sensor to sense the something, because we are talking on the outdoor environment point of view. So my sensing become a radar based sensing. So now you can rename this sensing and communication is integrated radar sensing and communication in the outdoor environment aspect. Now we can come on the radar sensing and the communication. What is the challenges and why we are going to do this? For example, everyone know that radars works on their own phenomena, communication works on their own phenomena, but if you see the behavioral point of view, both works on the electromagnetic phenomena, right. And now specific motivation I will see in the next slide. So we need a system that is capable of doing the communication at the same time as well as the doing the sensing at the same times here. If we are going to do this, we are going to achieve certain parameters. We will see much in more details later on. Now very specific point of saying one application I can tell you, and then we can see the motivations. Suppose that now everyone is talking in terms of the autonomous car, or the label autonomous car has a different label. Till now no one reach on the level 5. So we Tesla, and even though they are working on the level 3 and level 4 categories, what they have basically, or even though now very sophisticated cars also, they have a radar system, they have a communication system. The goal of the radar system with the car, that they detect the surroundings, and the goal of the communication system to connect the base station and nearby unit to do the communications to fulfill the requirement. Communications means that if I have a car, I need to press the brake, I need to sense something that okay 5 meter ahead I have something, I need to push the signal to my actuator press to the sensors to press the control the speeds, all this kind of communications, because everything is on the communication page. Now existing system has a two set of blocks. One is the communication hardware, one is the radar hardware, right. Now, if we have two hardware, obviously you can see both hardware their own cost, both hardware has their own price, both hardware their own weight. So, these are the kind of challenges there. Now, we are saying that if we are going to develop a technology where we are going to combine the sensing and communication, joint radar sensing and communication. So, we do not need a two block, we can develop one block of integrated sensing and communication, integrated radar sensing and communication. That block is going to fulfill the requirement of two block. If we are going to do this, we have the compact in size, we have the low cost, we have the low weight, we have the less power consumptions, efficient utilization of the spectrum also, and the low mutual interference, because if you have a two separate system, you have an interference constraint also there. So, if you have a single system, they have a the less interference aspect also. So, basically this is the benefit of doing the integrated radar sensing and communication. Now, very layman point of view, now we have two separate system, one is the radar system, one is the communication system. If we are going to develop the concept that okay single system, then what you can say, okay this is my radar system, this is my communication system. What you can do, both are separate system, this is what interference we are talking, the mutual interference between the systems also, right. So, the very layman point of view think that what are the philosophy that we can work. One philosophy that I have a two system, I can mount two system and work, they will do the same job, but with the challenges. This is this kind of mind methodology you can have the cohabitation. The second methodology, very layman point of view, okay I have a two system, that is enough. Sometimes I can use one system, sometimes I can use two system, I can avoid the interference. This is exactly what we have a called cooperation based. You can radar can cooperate with the communication, communication can cooperate with the radar. If we are going to do this, I can say that okay I can fulfill the requirement, but the challenge is that you cannot fulfill the application KPIs, because so if when you are using the radar on this time duration, you are losing the communication. What is the solution? That you can solution, then you need a design a co-design based system. Co-design based system means joint system, joint system that is capable of doing the radar, capable of doing the communication also. Now, the concept of joint system start with the concept that we need a single physical layer design. The physical layer start from the single waveform design. If you see on the research on the very basic point of view, that I need a system that have a joint system that is capable of doing this. This is what we call as an integrated system, and integrated system design start with the integrated waveform. So, I will give you the whole motivation regarding the integrated waveform. So, my research on this area is focused on the integrated waveform point of view. Now, coming on the integrated waveform point of view, very specific what is our objective. So, as I mentioned, if you see the automotive radar, because we are talking in terms of the radar. So, automotive radar works on the two separate frequency band, in 24 gigahertz band and the 77 gigahertz band. In 24 gigahertz band, they have 1 giga of spectrum available, while if you see on the 77 gigahertz of band, they have more than 5 gigahertz of spectrum available. Now, if you see the communication, in the millimeter wave, we are pushing also communication to the higher frequency. Existing millimeter waves also work on the 24 gigahertz band, but we are from the starting promoting that integrated system need to be work here on the 77 gigahertz band, because 24 gigahertz band we are not saying is not optimum solution, because you are going to use this as spectrum, but this is really limited. Here we have a lot more spectrum available. We can use this spectrum which is comes with the free of cost to improve this communication, which comes with the larger price. If your company wants to get the spectrum for communication, ton of the price need to pay. Radar spectrum is available free of cost. If you need to buy hardware, one time radar systems, you don't need to pay on the monthly subscription. This works on the monthly subscription basis. So, what our objective that if we go here, we have lot more spectrum available, we can use this spectrum to improve this, means using this spectrum to reduce the requirement of communication spectrum. if we are going to succeed this, then you can say that company need to pay less cost on the subscription basis for the communication spectrum point of view. So, now the motivation is here. Now comes that both radar and the communication work on the same physical phenomena of electromagnetic waves. So, why not same equipment, same spectrums and same signal can be used for both the purpose? Why not? Because both are the philosophy is the same, and now we are matching on the spectrum point of view also. So, why not we can use the same, and this is exactly what we are doing in our research lab, and this is the task that what we are doing to design a single air interface and appropriate signal processing, because signal processing change also, because now we have to take into the account of radar sensing, radar signal processing plus communication signal processing. So, the air interface with the appropriate signal processing, you can do this. Now, what are the key objective I am going to propose here? Design of the physical layer, demonstrating in terms of the KPI, both in terms of the say KPI of radar, KPI of communication, and then also the hardware development. So, we are not only limited to the conceptual point of view, we propose something, we also develop the hardware setup of this. I demonstrated this exactly this hardware setup in India Mobile Congress this year, and we get a lot of appreciation on this because we have participated not from academia point of view, is an open competition, we participated from there on, is called 5G hackathon point of view, and we selected from there on and we demonstrated this technology. We got lot of appreciation from the government, from the especially from the DOT also, Department of Telecommunications, for this aspect, and they are also open a path for us that we can put this observation into the ITU document, that this is what we are doing in terms of the integrated, worldwide lot many persons are doing in the integrated sensing and communications. So, we can also lead our path into the ITU document. ITU is the International Telecommunication Union, governed by the worldwide standard, right. So, now coming on the that if you want to design a system of integrated system, what is the challenge in the designing of system? So, first aspect to understand the challenge, and with the help of this challenge we will go on the conceptual point of view. What is the challenge here? Challenge start from that, okay, you have a two system. So, you have a system for radar, you have a system for communication, each system has their own KPI. Now, if you see radar system KPI is more towards the detection performance, I need to detect the object, I need to localize this object, localization performance, detection performance and recognition performance. These are the requirement on the radar point of view. If you see on the communication point of view, we always focus in terms of the robustness, bit error rate, packet error rate, blah blah blah. In terms of the efficiency point of view, both either in the spectrum efficiency or energy efficiency point of view. So, now we have a two set of parameter, one set of parameters dealing with the radar KPI, another set of parameters dealing with the communication KPI. Now, we need to build up a system going to fulfill both the KPI requirement, because individual radar system is able to do this job, individual communication is able to do this job. Coming on the two system into single system, still I need to satisfy this criteria while having the several advantages. The second aspect, second challenge is that because we are working on the outdoor environment and we are targeting on the vehicular communication aspect. So, you can see the channel is very fast, channel is the between the transmitter and the receiver. So, between the communication system to the car or car to communication system. So, channel is and car is moving. So, the mobility aspect is there. So, channel is very fast. So, under the presence of the channel, rapid varying channel conditions, and due to the channel rapid channel conditions, there is a problems comes in terms of the system impairment point of view. This is what we call as a carrier frequency offset and the frequency timing offset. Two major impairments come in general system on the system point of view, that okay, because we are dealing on the 2D systems where the time and the frequency involved. So when you have a mismatch into the frequency, in general way you can say the frequency offset is there. Mismatch in the timing information is called a timing offset. Under both the challenge comes with the mobility aspect also. So under this kind of scenarios, how we are going to deal this scenario, or you can say how your system is robust under this kind of challenging channel condition to fulfill these KPIs of the communication performance. Now just giving you this slide that to understand the holistic scenario of what are the waveform point of view in the world wise point of view, and then what we are doing exactly. So 4G and 5G basically more concentrated towards the OFDM and the DFT spread OFDM. OFDM is orthogonal time frequency division multiplexes, and DFT spread OFDM is DFT precoded OFDM. So they are adding one DFT blocks if you are we turn the research. So what is the philosophy of OFDM? OFDM has a subcarrier, one subcarrier with a certain frequency. For example, if you work on the 4G, they have a 15 kilohertz subcarrier spacing. If you work on the 5G, there is a concept of new radio. New radio bring the concept of the numerology. Numerology concept means changing the subcarrier spacing. The 5G say that okay, no, I have a 3 group of system: enhanced mobile broadband, massive machine type communication, ultra reliable system. I cannot deal with the single carrier spacing. Okay, what you can do? Sometimes you can use 15 kilohertz, sometimes you can use 30 kilohertz, sometimes you can use a different frequency. So this concept called a numerology. So new radio 5G waveform is nothing but a OFDM integrating with the numerology. So I will just keep on the OFDM point of view. So what is there? There is a subcarrier spacing, and there is a one subcarrier here, and they have a symbol during the subcarrier. So delta F is a fix. Even the new radio, delta has a three categories, but one sub symbols is spreaded in the one subcarrier here. Now what you can immediately realize looking this, okay, you have a fixed frequency symbols, frequency subcarriers, you are spreading your data into the time. Now if you look here, DFT spread OFDM, what you can say, okay, DFT spread OFDM fixing the time, spreading a data symbol into the frequency. Now you can say, I don't know there is a word or not, what you can say that okay, suppose that okay, so suppose that this is your channel condition, suppose that this is the channel I am saying into the time domain, this is my channel into the frequency domain. Now you can say that okay, if I have this channel, I can say individually this is a good channel, this is a bad channel. If I have a very bad channel, it's not good idea that I can use same number of symbol here, same number of symbol here, because here the getting the probability of error is larger, here getting a probability of error is lower. So probability of error in 2 is greater than the probability of error in 1. You can immediately say this. And now this freedom here, equal distribution is not a good solution. Same you can say on the frequency here, on the here. Now the point here that if you see on the OFDM, OFDM is allowed to do here, but doesn't allow this part. They have a fixed frequency, within a frequency you can do this. DFT spread allow this, doesn't allow this part. You have a fixed delta t, within a delta t dimension you can spread into the only the frequency component. Now if you see the GFDM, GFDM is called generalized frequency division multiplexing. This is this waveform is proposed by Professor Gerhard Fettweis. This waveform also got lot of attention during 4G to 5G also. So if you say what they bring, okay, no, it's good idea that I need a 2-dimensional waveform, that is delta t and delta f. I need not a constant here, I need a 2D. So they build up a 2D waveform where you have a delta f here, delta t there. It means 2-dimensional spreading you can do this, but the limitation what we have, the constant delta f constant delta t. You within this system you cannot change delta t and delta f. This is exactly the GFDM. Now, what we have, the one new waveform is OTFS. Lot of attention in the OTFS also is the orthogonal time frequency waveforms. What is the doing? Orthogonal is they are assuming that the signal is on the delayed upload domain, or basically the 2D multipass channel is the delayed upload domain, and then they are doing the converting band to the signal processing, converting back into the time frequency domain and doing the processing there. Delayed upload domain is going to do perfect job when we are going to do the signal processing into the delayed upload domain, but realizing the hardware into the delayed upload domain is really a challenging. No one has a solution regarding how you are going to do the signal processing into the delayed upload domain. If you are converting a delayed upload domain signal into the time frequency domain signal, or you can say that okay, I have a signal into time frequency domain, when I go near the channel I will convert from time frequency to delayed upload domain, when I go out of the channel I will convert again from delayed upload to the time frequency domain, then you can say the OTFS is not going to perform their job, optimum job, because of the limitation in terms of the signal processing plus hardware. Now, we are just assuming that OFDM is a kind of converting back from one domain to another domain, but still has OFDM has a limitation of delta t and delta f. With the key motivation but why we are rotated, just saying that we are converting from one dimension to another dimension, but limitation that delta f and delta t is still constant there. Now, one more waveform here is called, nowadays also got attention, is orthogonal chip division multiplexing, the OCDM. OCDM brings the motivation from a 3G based system, is CDMA based system. CDMA use the chip division and multiplexing also. Nowadays lot of application where need a low energy signal, kind of LoRa systems, kind of low power wide area networks applications, they use the chip division multiplexing. So, OCDM brings this concept, and we are saying that now my signal not is in the time domain, not in the frequency domain, is in the direction of chirp domain, still with the limitation that delta f and delta t is a constant. Now, we need to achieve this. So, we need a delta t1 here, delta t2 here, we need a delta f1 here, delta f2 here. Here we realize that if I know that okay, this is the bad channel, I can use less symbols. So, I can increase my symbol durations. Here I can compress this. So, delta t, and so I basically what we need a variable delta t and delta I depending on the channel conditions, and this is exactly what we propose. We propose the waveform, this is name is generalized adaptive spreading modulation. Very specific name, generalized means with this generalization I can convert back here, I can convert here, I can convert here. This waveform is a generalization of this part. These are the special cases comes under this category. Now, with additional generalized naming because of this part, adaptive naming, this delta f i's and delta t i's can be changed according to the channel. We need to estimate the channel, we need to this is called as the channel state information, we need to bring the channel state information at the transmitter side. Depending on the channel state information at the transmitter side, I can change delta f and delta t I. I will just later on show you how I am going to change this with the channel state information, and then I can change this. So, now this is exactly we propose the waveform, and we evaluated this waveform in the context of the integrated sensing and communication, because sensing has their own KPIs requirement. So, we can change the resource block depending on the sensing requirement or depending on the communication requirement. So, generalized adaptive because of the channel spread modulation is spreading the data symbols both either in domains or time and frequency domain. I hope this is idea is clear, that is very layman point of view. If you have a piece of paper, you can put everything, you immediately realize that okay, I need a system something like that. Then the job comes that how to do this, this is the research, but the requirement is clear. And then how to clean this? Okay. No, sorry. Okay. Now, we are going to test this waveform into the solution of into the context of the ISEC. So that's why the proposed generalized adaptive spread modulation GASM system in the context of integrated sensing and communication. So what is the integrated sensing and communication? You realize that I need some system that generate the integrated waveform. That waveform can do radar as well as the communication. So for example, this is my transmitter, this is my receiver. What I need to do with the same job, the signal I transmitted, they hit the object, they are going back here, or signal also going to have to do the communication. So I need to do the radar processing of the same signal, communication processing of the same signal. Now the point here, you can say the existing base stations, they do either transmission or the reception. Here we need to design a transceivers that is capable of doing the transmitting and the receiving on the same page. This is the just to demonstrate you the conceptual point of view. Now coming on the bit on the theory point of view, not much more complicated. So basically what we realize that suppose that this is my data symbol I have. Data symbols before the our proposed waveform. Now what I do, I added these parameters. This is what we are especially say that suppose that your data symbol into the frequency domain. So suppose that you started here, you do the modulations, you have a frequency samples here. Frequency samples I am spreading into the frequency. Now you can see the delta t here. So I am spreading this in the context of the delta t. So I know the delta t, and then I will spread the symbol how much, how less, how more, depending on this delta t. Now after this I have a frequency sample spreaded into the frequency, converting back using the IFFT. This part is exactly the IFFT block. So I have a frequency spreaded here, converting into the IFFT. Now I have the time. Then I have the so now these parts I have the so this is the frequency sample spread into the frequency IFFT. Now we need another waveform to convert into the spreading into the time also. We added another this parameter. That this now you can see this is the final equation. What the final equation has started from a symbol, spreaded on that domain, converting back again into another domain, spreaded into another domain. So we are adding both the domain, controlling our symbols in both the domains. Now
just on my one question, here is any specific reason to consider m square and delta f square?
No, exactly. So the specific motivation, because we need to control the sampling also, as well as the to make it compatible on the Heisenberg principle. Basically this concept comes from the, if you see the transformation, different transform generations, starting from Fourier to LCT or Fresnel Fourier transform. So this is the kind of tool we have already present in the signal processing. This is close to the Fresnel Fourier transform, but Fresnel Fourier transform has a limitation that they will do only e to the power pi by 4 spreading. So we extended basically the concept of the Fresnel Fourier transform in a very generic scenarios, and that's why we are saying that we are spreading either with this parameter. And this is the theory already exists with the Fresnel, so we work around that direction. Now we don't have exactly the same sampling theorem, because the sampling change, because we have a symbols spreading in both the domain. So you cannot say the same standard sampling of original signal will remain here. So the sampling of signal change depending on the spreading of your symbols. So now what we have the original sampling spreading into the frequency, converting back into the time, spreading into the time, my sampling change, my new sampling must be the parameter of both the domain, because if I know both the parameters, if I can control this, how I am going to control? With the help of sampling, because spreading is nothing more, but if I control the sampling, I can do the controlling the spreading here. So, this is the mathematical point of view of the proposed waveform. Now, as I promised that we propose a generalized waveform, so good to show that how we can go on the special cases of the proposed waveform. So, the first special case is OFDM. So, you can say that if you are going to put sigma t and sigma f, we will later on you can realize what is sigma t and sigma f. Sigma t and sigma f is nothing but what the sampling we are going to achieve. This is the highest common factor from this spreaded parameter. This is already present here on the sampling. We are changing, so now you can say we have a 4 variable, so delta t, delta f, but we are not changing delta t, delta f because I am going to lose the sampling. Sampling has their own restrictions. So, we have an additional parameter that change according to the sampling, and this is exactly our spread parameters. You can say the sigma t is spreading into parameter into time, sigma f is spreading parameter into time. So, now you can say that this is the special cases of the OFDM. If I put a 0 on both the part, I will remove this equation, and then what you have remain is OFDM. Now, the one more waveform we already work here in the past regarding the 4G to 5G is called a fractional Fourier wave transform. This is also the special case that if you put sigma t and sigma f as a COT function, then you can achieve this special case. Now, the new waveform what I say is orthogonal chirp division multiplexing. This is also get lot of attraction. So, if you put a sigma t, sigma f phi, now you can see immediately this phi is a constant. Then you can achieve exactly the OCDM, but this phi is a constant, and that is exactly we are trying to solve with the spreading. So, these are the special cases of the proposed waveform. Now, the point start here that okay, you know your sigma t, you know your spreading into the time and frequency, how you are going to achieve this. This comes under the optimization problem. What we have basically, we have the SINR of signal. What are the parameter I need to control? The parameter of radar parameter of the sensing communication parameter. So, the constraints now on the both radar as well as the communication. Under this constraint, obviously the constraint you can say exactly the same: detection performance, localization, spectral efficiencies, probability of detection, probability of false alarms, all these standard KPIs from the communication and the KPIs from the radar. So, these are our constraints, because I need to achieve these KPIs that going to fulfill for both the cases, and while having maximizing the SNR, because SINR maximization has a capacity maximization, and the communication engineer point of view, our objective is to have a maximizing the capacity point of view. So, this I am not going on this technical point here, but the constraint here you can say immediately maximizing the SINR under the constraint of achieving the KPI requirement of both communication as well as the sensing. Now you can say on the broad way, this is our architecture of our proposed waveform. How this architecture is look like? This is exactly you can say this is the symbol I have, spreading into the frequency, converting back into the time, spreading into the time, and then transmitting here. Now, with the same signal I will do the radar processing. Existing communication system does not have this block. We integrated this block, that the same signal I will do the radar processing. What is the job of radar? Radar job is to detect something, to give us the information about what is the location of the user. So, this is general information on a match filtering we can compute the autocorrelations, finding what is the delay Doppler estimation of this object, getting the what is the velocity profile of the object, what is the location of the object. And the same signal we can also do the communication processing here. Standard communication processing, because we are doing the this part I need to reverse back here, on the communication perspective point of view, but adding the communication sensing part here. So, this is the proposed concept in terms of the block diagram here. Now, as I mentioned before, now we have the with the same concept, same waveform. Now I have to have a two set of result. One set of result regarding the radar performance evaluation, another set of result regarding the communication performance evaluation. I need to achieve best on the both the cases. Now, this is the set of performance in general we evaluate for a communication point of view. Communication we always evaluate in terms of the bit error rate, packet error rate, right, and a communication performance. So, bit error rate versus the signal to noise ratio. Now, here we compare again the all the existing waveforms, the different waveforms. So, you can see here that as lower bit error rate we have, that is much better system. So, we want to reduce the bit error rate, so that I can increase the robustness of the system. Now, you can see on the very special cases, for example, this is our proposed bit error rate. Now, you can compare for in a single SNR, you can say that okay, our system has a lower bit error rate. For example, if I compare on 25 dB, you can say that okay, proposed system has a bit error rate of 10 to the power minus 3, close to that. If you compare on the OCDM on this domain, you can say the OCDM has a bit error rate close to the minus 10 to the power 2. If you compare okay, where the GFDM is, GFDM is this part here. GFDM has very close to us, has a achieved the bit error rate, but is always higher than us. So, we receive the lowest bit error rate in terms of the SNR. Now, the one aspect more comes here. What about the impairments? Because the SNR, what are the impairment I mentioned before? Impairments in terms of the frequency as well as in the time, because channel is fine, we have the time varying channel here. These problems also the what is the carrier frequency offset problems, what is the frequency offset problem. So, we evaluated for first case no offset, if there is no challenge, every waveform has the same result. Now, if you introduce the challenges, then the system robustness comes there, and this is the different offset we evaluated the system. I am not going much description here, just giving you the idea that okay, while observing this under the impairment, the proposed waveforms has a much better bit error rate. Why? Because of the nature of the system. Now, this is what we plotted, like the bit error rate versus the carrier frequency offset. Again, you can say that okay, where is our proposed? No, dash black line. Yeah. Now, you can see the robust, even though you are increasing the carrier frequency upness, this waveform has a better robustness as compared to the red one with the OFDM. So these are the simulation result. We are doing also the analytical. We have submitted the paper there, so it's still not published. Now, this is the first part of result, where we just show you on the communication performance. Now, the second set of result where we are going to show you on the radar result. So, if you see on the radar, they will evaluate the performance in terms of the ambiguity function versus Doppler, ambiguity function versus delay in the radar, and their objective is that I need to minimize the side lobes. So, I need to minimize these levels in the lower level, so that I can receive a less power from the neighboring. And here again I compare with the existing system, OFDM, GFDM, OTFS, OCDM and other waveforms. And here in this scenario you can also compare that both in terms of the Doppler, both in terms of the delay, we have the lower average side lobe level as compared to all existing waveform. So, now with this result, at least we sure that this kind of waveforms has a more suitable both in the context of the communication as well as the context of the sensing, achieving the best performance in both the scenario without hurting the performance of others. Because if you see the OFDM, you can achieve the best performance in the communication, but you are limiting the sensing performance. If you look on the general philosophy of the radar processing, they work on the chirp based signals. Chirp based signals has a better in terms of the sensing performance, very poor in the communication performance. Objective is to achieve both, and that is why we work on this proposed concept. Now, after the simulations we did a technology demonstration point of view. technology demonstration in the real time that we have software defined radios. What we are doing, we are capturing the image. We have already the simulation of setups. We use the SDR, and thanks to Nitish ji, so he is here and we have a lot of discussions. He provided us the SDR also there, and and then we did converted our theoretical aspect into SDR and transmitted over the air. Consider that we have a 2 SDR, so we always rely on transmitting of signal over the air, and another set of SDR where I am receiving the signal from the another SDR, doing the processing here of our concept system and reproducing the image back. So we have an image, doing the processings, sending the system over the air. For example, I have my receiver, another room, receiving the signals and doing the processing and converting back into the video. Now if you see here, that this is image, for example, we capture here. Now we pass this image with all existing system, OFDM based system, GFDM based system, OTFS based system, OCDM based system, and this is the our proposed one. Now you can say this is not because of the signal processing error, this is not image processing, this is error because of the bit error rate error. So person say that okay, this is the image processing, this is not image processing, is the because this has a higher bit error rate. So when you receive the signal has a large bit error rate, the bit error rate impact you can see the quality of image. Now what set of simulation result you can realize here, you can relate the quality of image also from there on. You can say that this has a bit better than this has a bit better than this, but is still has a error. And now this is our proposed. We have also certain error. For example, we have also the error of 10 to the power minus 3. We cannot say that we don't have a 0 errors. So we have also the error, but now you can see that we have a much less error as compared to the proposed system. This demonstration we did it into India Mobile Congress this year in the real times. We are the part of 6G workshop there and demonstrated this philosophy of integrated sensing and communication there. So we have a set of publications and patent on this technology in India, as well as we are organizing a special workshop in NCC this year. NCC is National Communication Conference held by the IITs. So and this motivation comes again from the IMC. So I meet there Professor Bhaskar Murthy. He is a general chair of ICC this year. He is a professor from IIT Madras. He is a director of IIT Madras also. He motivated me to give one session workshop in NCC this year on this concept of integrated sensing and communication. And I am also presenting the tutorial next year in Belgium regarding the same concept of integrated sensing and communications. So this is my first set of work. I did it in the context of the 2030 point of view. Any one of you are interested to explore on this area on the research of integrated sensing and communication, not only the theoretical aspect, not only the simulation aspect, the core hardware, we are also working on the VHDLs languages to develop the hardware. Next step what we are doing, I have a project with 6G flagship group in University of Oulu, Finland. So we are now integrating this concept with the ORAN functionality. ORAN is Open Radio Access Network. Now you can see lot more attraction nowadays in the ORAN also if you just Google it. So we are building the standalone system of this demonstration, integrating with the ORAN point of view. Right. So this is my end part of presentation on the first aspect of integrated sensing and communications. If you have any question on these parts, we can have a, you can ask. It's not necessary only on those 2 points because ISAC has a different use case. So 3GPP just started the feasibility study of ISAC. So they list down what are the different feasible use cases of the ISAC. So they use case from the vehicular, use case from the health, use case from the different areas. Because I'm work on the vehicular aspects, that's why I put radar as a sensing parameter. But if you see on the indoor environment aspect, you can say that okay, I have a ton of sensors, or you can just example smart manufacturing. What is the key challenge of the smart manufacturing? That okay, you have a big hall, lot of robots, machine are moving, channel is changing drastically, some obstacle is coming. How maybe some has create jammers to block your manufacturing setup. What is the solution you have? No solutions. Trust me, in the world wise, no solution is there. And one of the possible solution with this, you can have a set of sensor network. The goal of sensor network is to sense the environment inside the hall. Now inside the hall, and also predict that okay, some kind of interference is coming from some other direction or not. While having this knowledge of sensing, what you can do, you can trigger your communication requirement. Okay, no, for example, this is a hall, I have a sensor here, I can assume that okay, some interference coming from here, I will go on my resource management in the communication, say that okay, reduce the reliability of this part, improve the reliability of the other parts. I can save my manufacturing setups there. Because when I was in Germany, I was worked with the Bosch company exactly on this framework to set up manufacturing setup in the context. So ISEC has a potential application also in the industrial communication aspect. Yeah, there is a lot of generalized fading channels. So we can evaluate the performance. So that different aspect also. But it's good also for a research point of view. What we are thinking that evaluating performance in the real time scenario. This is the demo what we have is not you can say the real time what we are developing in the next phase of demo. We are putting this SDR into the one car, or you can say toy car, and we are running this toy car and making known interferences. That okay, let's see that my system is robust to detect that interferences, to deal the interferences. The next phase we are working on this aspect. This part of work I'm very close to the Geo. They are interested to have you can say in a way the consultancy project with me on this project. Geo wants to channelize this topic for their industrial point of view. So we are very close with the Geo on this topic. Close to finalize this. Huh? Yeah, because I'm main motivation to join here is to entrepreneur mindset, is to promote the research in terms of the either startups or with the industry, not on the theory limit point of view. At the end I can do it. I will also give you the sense, because India has a true potential there. Lot more students are here, so laborious, so we can do that. We works on this startups. One more story I can tell you just for 2 minutes. So when I was in Germany with the Professor Gerhard Fettweis during time of 2019, that time the Maisi MIMO antenna was one of the highlight, and Geo was to acquire the Maisi MIMO antenna. He did not. He was in the discussion with one of my professor startups there. They have a several round discussion that this Geo wants to acquire this Maisi MIMO antenna what a startup are developing. I was in the part of the discussion team also because I was a group leader there. So at the end they demand so huge amount that Geo did not give them opportunity. Now if you just Google it, there is a startup was Eris in 2018-19. Now this startup is acquired by the Xilinx. Before Xilinx business is not in the Maisi MIMO antenna. Xilinx business is to produce the FPGA boards and all. But now if you Google it, the Xilinx, because of that startups, Xilinx comes into the business of Maisi MIMO antenna system development. I was very closely to observe that on this kind of deals, and I have true potentials. What we realized that I saw. So if you Google it on the TU Dresden, Dresden is one of the old city in Germany, not very industrialized. Because of single professor, he has at least 20-30 startups acquired by all bigger companies, Google, NI, Xilinx, and now if you see the Dresden is the hub of the technology in Germany because of the single professors. All is a startup acquired by the higher companies. They have the office there. They are continuing the research from there on. Now, good. So I will just go on the beyond 2030 vision. That what we are doing. Again, very specific on the quantum mission point of view. So if you see, India launched a quantum mission recently. So we are in the discussion with the team also working on the DST on the quantum mission. So to promote the quantum technology. Now, because we are a communication engineer, and from the first phase you realize that I have expertise on the quantum sensing and communication. So I will narrow down the same quantum technology in this domain of sensing and communication aspect. So this is the team, the PhD student working on this topic of the quantum. Now, if you see on the quantum communication, the first things start that we need a quanta that can use for the communication. One more limitation I can say, in India, lot many companies or government also claiming that they have a, even though the ISRO I am claiming obviously, they already demonstrated the quantum communication, but this is not a true story, because what they demonstrated, the quantum story, that okay, they have a physical transmitter, physical receiver. What they do, they have one secure key, this is called QKD. They are sharing this QKD between the transmitter and receiver. Transmission is still the classical, the power line optical communication, just sharing the QKD. QKD is a security key between the transmitter and receiver. What they did ISRO, this is a quantum technology. This is not a true potential of the quantum technology, but we realize, because if you are claiming this is quantum, you are sending the quantum here, photon here, receiving the photon, doing the quantum processing. But ISRO did it and claiming that this is a quantum, but it's not in our sense is true.
So for the quantum communication, there should be line of sight between transmitter and receiver.
Not necessary. Now you are again focusing on the quantum in terms of the photonic point of view. Lot more research in the world wise did a quantum near the photonics, or you can say the optical frequency ranges, but no one did or even no theory of the quantum into the microwave point of view. And if we want to realize true potential of the quantum communication, quantum sensing, we need to go on the microwave. And if you just go, check, China is already developed the quantum radar. China has developed the quantum satellite, and this is very crucial for India, and that's why India promoting to have this quantum technology in a defense, very specific on defense point of view. I can tell you one line story. For example, as I mentioned, probability of detection versus SNR. If this is a probability of detection versus SNR for classical communication. Just suppose that Indian government wants to detect the Chinese fighter jet. What the technology they have the classical technologies or classical radar. They can say that okay, if I receive a 25 dB SNR, I can have ensure that probability of detection is 0.6. Or even though if I can increase the SNR of 30 dB, I can ensure that I can detect 0.9 probabilities. What is the true potential of the quantum here? Even though you are very 0 dB, very close to minus also, you are able to detect at least more than 0.6. And now or 10 years later, India needs this quantum radar, because in order to compete with the China in terms of the defense point of view, you don't have any solutions. Classical system, this is not because of the, this is key because of the Heisenberg principle limitations. You cannot get better than this. You need to go on the quantum to have this figure, and this is also lead to the path of the green communications. Now coming on the quantum communication point of view, so if I want to realize the quantum, what I say, I need to transmit a photon, I need to receive the photon wirelessly, not optical. Then what I need to understand first, how to do the processing of this quantum. So, the first start the quantum information processing building block. Now, if you see the quantum information building blocks, what are the steps there? I have a photon. Photon generally has a 2 spins. So, for example, one more line I can say, for example, I have a photon, I can say that okay, either I have from plus 90 to minus 90. In digital communications or in communication, we say information in either 0 or information in either 1 to 0 or 0 to 1. Here the information carries between minus 90s to plus 90s. Very similar approach, nothing change. If you want to change the information, you can change the photon phase from minus 90 to the plus 90, you can save the information. Is the same, you can relate this from 0 to 1 or from the 1 to 0. Now, with single, what is the key aspect? Single photon can do the change the phase. Now, the point comes that how fast you can change the phase, how fast you can detect the phase change, then you can increase the capacity of a quantum signal, because the whole information is moving from minus 5 to plus 90s. So, the aspect that you, if you are going to do this, you are going to achieve this. Now, the first block, I have to state preparation of the photon, then I will transmit this photon, then I will measure the photon on the receiver side to detect. Same you can say okay, transmitter, receiver, the channel part here. The photon carry by the channel of U and the reception of this. Now, the first aspect here comes that if you have a photon, transmitting the photon, receiving the photon, there is a like chance there is an error in the photon. Though the first philosophy comes that can we do the error correction techniques in the photonics domain or not, because first aspect that because this channel comes and photons are very sensitive to the external environment factor. So, though the point come here that if there is an error in the photon, how I am going to do the correction of this error, because when we are going to do the correction of error, then only if feasibility that we can use photon for the communication point of view. Now, then our first studies start with the quantum error correction. If there is an error in the qubit, how I am going to do this? So, you can immediately say that I have a qubit, same philosophy of the classical communication, I add in the some syndrome bit, extra qubit, doing the encoding, transmitting over the quantum channel, doing the error correction, error detections, and detecting our receivers. This is exactly what we are doing in terms of the quantum error corrections. Everything is on the photons, not with the classical. Now, you can say this is the literature available regarding the quantum error correction. You can say the physics guys is doing the quantum error correction not from now on, from 1995. So, this field exists only in the context of the physics point of view, in terms of the optical frequency range, not on the photonic frequency range, having the limitation of this. So, these are the kind of different techniques available for quantum error corrections. I am not going to on the individual details, but I can tell you one line philosophy point of view. All the techniques has a philosophy that okay, you have a qubit, you have a syndrome bit, this is the extra bit you are adding. With the help of this extra bit, you will doing the encoding and you are doing the error correction, error detection. The philosophy that this extra bit you have, and this extra bit does not carry information, the extra bit going to help to do the error correction and error detection. This is the philosophy of all the research paper. Someone can do single, someone can do the multiple error, someone can do the bit flip error, someone can do the phase flip error. So, different methodology. Now, here on I can tell you what we did it difference. Our thought start that if I am transmitting this qubit and syndrome bit and via the channel there is a likely chance also that the syndrome bit got also an error. We cannot ensure that the syndrome bit always have a correct bit. If syndrome bit feasibility, that like a Q bit, syndrome bit can also be an error. So, this is the what difference we introduce, that we are considering the syndrome bit is an error, then still we develop a encoding and decoding techniques to correct that errors.
So there is any simulation model where our student can work?
There is simulation model, but it's not open source, because we put a lot of efforts to identify the paths. Trust me.
Is it in MATLAB?
No, no, no. It's not in a. We use IBM quantum computers and integrated via the Python. But if you are interested, basic codes I can provide you also. At least the literature codes. QSKit. Yeah. Okay. So this is the general techniques works on this quantum error correction point of view. Now I can say you on very layman point of view how it's working of the quantum errors. I have a cube, as I mentioned. So photon has a phase from minus 90 to plus 90. So either I am moving from a qubit 0, 0 1 1, or qubit 1 from 1 to 0. So either I am moving on this direction or I am moving in this direction. So I am just carrying, now my information signal consists of either this part or in this part, from qubit 0 or qubit 1. This is in the quantum they call as a qubit, qubit 0 and qubit 1. Qubit consists of from transition from plus 90 to minus 90, qubit 1 comes from the transition from minus 90 to plus 90. Now the same philosophy I mentioned. Now I have my, this is my this qubit is going to carry my message. So this is my message qubit, you can say. This is my syndrome bit. Now I am going to add the message qubit and syndrome qubit via doing the encoder. So this is my message qubit, is basically alpha and beta are the probability of the states, or you can say the alpha and beta are amplitude, then alpha square plus beta square is equal to 1, because you have only two probabilities, from minus 90 to the plus 90 or plus 90 to minus 90. So alpha square and beta square is equal to 1. These are the corresponding probability of the state. You are changing from qubit 0 to qubit 1. Now depending on alpha and beta you have an error also. So this is my message qubit. I am adding this extra syndrome bit 0 0. Then you can say that okay, after adding the syndrome bit I have alpha, this is my message bit, this is two syndrome bits. Now I am doing the encoding. So this is the you can say in general form, this is called as a C0 gate. C0 gate has a specific structure. C0 gate is basically the quantum develops in the IBM framework. So with the kind of realization of the quantum using the again the same with the gates level. Same on the digital we started with okay, how this NOT gate work, how the AND gate work, how the OR gate works. So same here goes on this direction. So I am going to do so message qubit I am going to encoding with the help of C0 gate. What is the C0 gate philosophy says? Same like NOT gate philosophy is that if I have a 0, I have 1 here, then C0 gate philosophy says if the first bit is 1, syndrome bit will change. Now this is my message plus syndrome bit, this part is my message signal. Now here I am passing this signal to the C0 gate, that first bit will 1, then the syndrome bit will change. Here first bit is 0, so I have as it is 0, here my first bit is 1, then my syndrome bit change to 1 1. This is encoding. Now I am sending over the quantum channel, we are introducing the error. Error means that this message bit has an error, so this 0 become 1, this 1 become a 0. Now you can say that this is the what we are going to receive. What we are going to receive has an error in the message bit, because this is the message information. Now you can say we did not introduce error in the syndrome bit. this is a state of art work I am presenting here. So now message bit has an error here, syndrome bit is as it is here. Then now coming on the error detection and error correction point of view. Again error detection I am using again the C naught gate, philosophy is the same. If first bit is 1, syndrome bit change. So here first bit is 1, my syndrome bit change. First bit is 0, syndrome bit will as it is. Then I am doing the error correction with the CC naught gate. CC naught gate says that syndrome bit are the same, then first bit will 1. Here my syndrome bit is 1 1 same, then my first bit will change. If syndrome bit is as it is 0 0 same, the first bit syndrome bits are the same, yeah. So syndrome bits are the same, then first bit will change here. So syndrome bits are the same here, then first bit change here. This is the classical state of art in the quantum error correction point of view, with the limitation that we are not assuming that there is an error in the syndrome bit. This is general we call as a bit error, bit flip error. Bit flip error because of the quantum channel this bit is flipped. Now this is what we propose, that we have a bit flip error and the phase flip error. I did not get the time to do in the PowerPoint point of view, so I take a notes directly here. I am not going on the proposed techniques on the technical discussion point of view, but here we one aspect you can say that we added many more syndrome bit which is going to help us to further detection even though few syndrome bit got an error. So this is circuit we build up and the theory along this. I mean we mathematically also prove that if we are following this we are able to correctly decode my message qubit. So this work we basically submitted a paper, propose a novel techniques for quantum error correction with the low implementation complexity. There is a conference next year beginning in the Milan. So we propose the conference, this paper concept there, but we have many more publications coming in this direction in the quantum error correction, quantum radar technology, quantum sensing and quantum communication point of view. Even though here you can see the only one person is working, but I have a different collaboration with the Europe, US and with the companies in India also. So we are working. Now coming on the future scope of quantum error correction, here I am very specific say. So you can say the quantum error correction has a role in the quantum communication also, because you are going to send a quantum, there is a high chance of error. There is a quantum error correction role in the quantum sensing also, quantum error correction role in terms of the quantum computing also. So that is why we started the first part to hit directly on the quantum error correction, and then from there on we will narrow down our area to sensing and the communication. So this is what I am. By the way, we are also organizing a short term course in IIT VHU beginning of next year, very specific on the introduction to quantum communication and machine learning. So those who are interested to be part, this course is going to taken by the at least renowned professor from Europe, and also they are coming on the physical mode. At least one of my supervisor, PhD supervisor is also coming for attending the for giving some lectures, and one professor from US also is coming for this course. Not one. Yes, so there is a cost to register, but is very less. Is very less, but we will provide accommodation and everything free of cost. Is very less. Even though someone wants, we have the feasibility to reimburse also. So at that case also. But my more motivation to penetrate this topic in a general research environment on the quantum for personal point of view, that we can what we are working can we have a more visibility point of view. And that is one of my motivation come here also to promote about this course. Our objective is to not have a earning point of view regarding this course, to be very honestly, but to bring the our idea into the research phase. Just one of this aspect. So yeah, for second part I will stop here. If you have any question regarding the quantum communication, sensing, computing. Actually, the spin of the photon. So if you see what is the so for basically the photons or you can say the not only the photons or any atoms has a spin. Now the spin means same what we are saying the electrons atoms. Spins comes in their pictures. The phase which means the spin of there. Now I didn't go on the technology of quantum. Basically quantum works on the philosophy of two core philosophy. 2022 Nobel Prize was based on the photon entanglement principle. If you just Google it, 2020 Nobel Prize received because of the quantum entanglement. They demonstrated the quantum entanglement, and quantum entanglement is one of the principle is going to help the communication. I can tell you what is the quantum entanglement. So suppose that I have a transmitter here. Sorry, अभिषेक जी मैं मीटिंग में आपको कॉल करता हूँ थोड़ी देर में. So what is the quantum entanglement principle here? Suppose that this is a transmitter, this is the receiver. What quantum entanglement principle says that you have a photon here. If you know that this is a qubit 0, if you have any source that is able to detect this is a qubit 0, in real time this will become a qubit 1. You can say establishing the connection between transmitter and receiver has a 0 time. This is exactly the entanglement principle says, and this is exactly what we are doing in to improve the quantum communication. If I have any source, for example, I can detect that this is a qubit 0, by default I can assume that this is a qubit 1.
So is there any technology by that you can detect the spin of the electron?
Yeah, so in photonics, optical range, there's lot many devices that you can use for quantum generation, quantum detection. In RF band, in optical frequency band, because optical frequency bands are low frequencies, very good to stabilize the photons. Stability of photon is really challenging. If you go on the higher frequencies, microwave, you need a cryogenic cooling. And that is why you can see the Google quantum computer shapes, they will put a minus 50-degree temperature because of this quantum, because they wants to go in higher frequency, because as soon as you are not going into the microwave frequency, you are not realizing the potential, but the key challenge that the stability of the photon.
So as our electromagnetic waves travel from one distance, one part to another part, it becomes wave.
Same there also. This is called a noisy environment, and that is why we call as a error in the photons. This is called quantum errors.
There is path loss.
No, there is no philosophy exist in the RF part still. There is no physics. So we are in discussion with some core physics persons from BHU also, not from IIT BHU also. They did a PhD much before my birth also. So they from last 10 years, before I am coming on these topics, I just discuss from them with last 2-3 months on there. They started building a theory regarding the quantum in RF frequency range. There is no theory exist in the quantum RF frequency. Is very good to also on the theory. Those person who is working on the core physics, they can explore on the theory also. And that is why I am saying that just to establishing this principle, 2022 Nobel Prize they win it. Google it 2020 Nobel Prize, the main contribution is to establish the quantum entanglement philosophy. Any other question here? Okay, so now on the third topic, I will go. Third research area that we are working on the molecular communication point of view. We do not have much here to show on the molecular communication. Two aspects that we are quite new here. I recently started this topic on the molecular communication, but leading to go on this direction. So just giving you the brief sense that what the philosophy we have in the mind and what we are thinking, that how we are going to approach this problem on this direction. So we are going to say that if you have any molecules or any atoms, what we have, they have a the molecules that are spreading here. So we are using this phenomena that emission process we can use as a transmitter. Emissions of the molecules from any source, that if we have any source that can emit the molecules, or for example if I have a body that can generate some kind of molecules, then we can use this part as the emission process for us as a transmitter. Obviously if you have a molecules that emit, obviously going to spread. This is what we call as a diffusion process, we call as a channel part. Some molecules may be the is not going to the part of our reception boundaries, and then the reception of the molecules in the receiver part. We are going to deal this part into the DNA recognitions point of view. And one more aspects we are here, that we are going to combine these molecules with the photon. And if you see the word wise, the leading challenge into the DNA recognitions of this, like the processing of these molecules. And once we are able to establish this, the philosophy of photon here, we can bring here on the quantum molecular communications aspects, and then we can use this application to do this. So molecular communication, as I mentioned, is work on the philosophy of diffusions as a channel, emission as a emission of the source, and then we can use the kind of encoding process here, kind of decoding process here, a kind of channel that we are going to combine here. This is the general philosophy I have. I am just not going to more here on the molecular communication point of view. Now very specific I am going to give you regarding our research vision point of view, what we are thinking in the research and why we are here, and promoting our research. And so from starting, if you realize that my research lab name is ICC lab, Information Control Communication Lab, and this is exactly the motivation comes from here. So we are doing the research, not only the communication, so we are doing the research while combining the control, information and communication. And that's why we established this lab called ICC lab, in Information Control Communication. Now if you see the kind of application, so kind of application, industrial communication, vehicular applications. I need to understand the philosophy of the control. Philosophy of the control means what is the kind of sensor I need to place, what is the rate of the data rate of the sensor, what is the position of the sensors. This is philosophy we need to understand. Please do not circulate in this. Yeah. So because I am using always from my marketing point of view this slide. So and then so we need to understand the fundamental concept there regarding the control point of view. Now impact of the information comes like understanding the behavior of the systems. This is comes on the information, and then the communication comes there. So the communication is not standalone, needing to understand the philosophy of the control, behavior plus communications. This is the same philosophy can go on the quantum, then same philosophy can go in the molecular, on the classical communication point of view, and this is exactly what we are predicting the future wireless requirement. Now one more glimpse I can give you, what is the market opportunity in this direction. At least no one can give you this figure, we have a lot of effort to, and this is a true figure you can say. Healthcare market in India. The current market size of in India is healthcare is around $150 billion. The current global market of healthcare, this healthcare market is not a market in terms of the nursing and other, to the very specific where the technology involved, development of the devices and all. 2 trillion market there, and this market is growing 15 to 20% per year. And okay, so no, okay, this current market size is only the 150 billion. I think there is some mistake. What we are predicting that Our current contribution in 2 trillion with 150 is 7.5%. We are predicting that if we are going to enhance at least same on the device development, we need to understand the sensing plus communications together, then we can improve our technology and we can increase our coverage up to 25%. If we are going to cover up to 25%, we are going to cover the market from 2 trillion to 500 billion. And similarly, the smart manufacturing market, current Indian market is only $7 billion. Global market is 480 billion. This market is growing 8 to 10% per year. If we are going to again do the enhancement in our research, we can cover current value is only 1.4%. The 16% is there. Similarly, the mobility market, this is the vehicular industry market, 3 billion markets, global market is 150 billion, 10 to 20% growth is there. Our present contribution is only 2%. Smart grid market is going to be in the future. Government is pushing a lot the smart grid, and we have a true potential of power line communication also. So while combining again the sensing and communications there, the current market in India is 500 billion. This market is growing worldwide 25 to 30%, and that's why India is pushing the smart grid because of looking this figure also, and more than 1 trillion market opportunity. Our current contribution is only 0.5%. We can enhance this also. So if you see that under this use cases, our current market we are targeting only $165 billion. The total market size we can advance in India at least $680 billion. If we target the global market I just multiply 20 times the Indian market. So we can target $1.3 trillion market while developing this advanced research. Maybe you feel this number is imaginary, but I'm sure because it's not realizing in one step. As a researchers, we are always looking much ahead on the beyond on this direction. So this is with this motivations we are also promoting for startups. You can take any verticals. You can come with us. We can provide you the support. So at least also the world renowned groups also to investigate your true potential on the entrepreneurship also. So this is all regarding my discussion on the research aspect. Now one aspect, so on the startup aspect, if I can to highlight you, so in India there is a huge demand of the startups. Now you can see the storyline also that success rate of a startup is very less in India. That true also everywhere, US, Silicon Valley also, or also in Europe. But this is the true concept of the startup. You cannot assume that 100% of startup will got success. But if you are working really on the technology innovation point of view, you have a true potential there, because it's not necessary that you can come into the because as a startup point of view, your job is not to build something, come into the market and compete with the existing player. Your startup point of view, your job is to bring the novelty, bring the innovation, demonstrate the innovation, motivate someone to acquire this concept. And their person's job is the regular marketing jobs. They can do the promotion of the, technology. That is the better way. The main failure of the startups in India, in our understanding point of view, because the company is developing something, they are thinking that they can go into the market, they can compete with the existing customers, or even though they have a lot more novelty, because marketing and business job is very complicated and need a lot of funds, lot of infrastructures. Even though I have one medical, for example, I am telling you my truth. So we started this startup on the ATAL Medical Tech Solution Private Limited in 2016, and we thought that okay, we can develop concept. I can tell you, if you go on inside the ICU, what is the challenge? That you have a big machines, lot of wire connected to the humans, right? Two limitations. One, mobility is very difficult of the patient. If government or any person want to set up ICU in the rural part, they need to bring the infrastructure in the rural part, and that is one of the limitation, that less number of ICUs exist in the rural part. because need a lot of infrastructures. With this motivation, we started this company that okay, we will develop a wireless solution for that, ensuring the reliability of the system. Now we first develop the concept. We received several funding from the government, private also, and then we did also the pilot testing in AIIMS Delhi. We thought that we will bring this technology into the market. We discussed with the Philips and other companies, and we fail on that. That okay, because that okay, company saying that okay, why we can do this regarding the acquiring of this technology point of view. Two reasons. When I go in the doctor and convincing them that okay, Apollo hospital for example, you have a big center in Varanasi. If you want to set up a small center in Sonbhadra, you can get a market coverage. You don't need to put a high sophisticated doctor, and then no need to travel from Varanasi to Sonbhadra. In Sonbhadra, a small place, you can have some virtual some machines wirelessly. Some paramedics can go there and they can do the checking of the patient and all. The first limitation there, the ICU is really critical. Doctor and medical persons are claiming that if suppose that in worst situation person will die, who will take the responsibility? Company will take responsibility. Doctor sitting in Varanasi cannot take the responsibility. Is very dangerous. So then our focus changed. That this is just a conclusion, but they receive multiple feedbacks. Even though after development of this technology demonstrated in the multiple places, they bring the concept of the okay, we cannot target the intensive care unit. Either some company can acquire our technology and can there do job. Then we bring on the personal care point of view that, but in personal care market, lot of Chinese product are there, lot of Google Watch and all watch. As an engineer, we cannot compete this. As with the China on like okay, I cannot prepare a smartwatch of 1500 and they can do my BP and everything's heart rate and all these things. So, but it's okay, it's a good learning for us, and we are investigating many more directions here. Government is promoting a startups, lot more funding available for government. If you have a concept, government has some nodal institutes called seed fund grant from the government. They are giving a certain amount of money for a period of 1.5 years. You can prove your concept, develop something to demonstrate. With that concept, you can bring into the more collaborators, more bigger funding opportunities. You can interact with the bigger funding opportunities for this. So it's really nice area, good learning point of view, and good to deal on the marketing point of view also. So thank you very much. And if you have any questions regarding all the talks.